Alright, trying out a new mic. Hopefully this records correctly. Let's go over chemical versus physical changes. Alright, so let's look at changes in matter. Working with properties and changes of matter. Everything is made of chemicals. So when you hear people, especially in California, saying they don't like to drink something because it has chemicals, they don't like to put that on their skin because it has chemicals in it, everything has chemicals. You, your food, the air has chemicals in it. A chemical is any substance that has a definite composition. It is always made up of the same stuff no matter where the chemical comes from. Example, water, carbon dioxide, oxygen in the air, polyethylene. These are all chemicals. A chemical reaction is the process by which one or more substances change to produce one or more new substances. So a substance being transformed into another substance, or multiple substances combining together to produce another substance, or a substance breaking apart into multiple new substances. These are all examples of a chemical reaction. Example would be lighting a candle. So in making a cake, you would add table salt, also known as sodium chloride. Sodium atoms and chlorine atoms mixed together, bonded together chemically. Sugar, also known as sucrose or table sugar, has 12 carbon atoms, 22 hydrogen, and 11 oxygen. Vanilla has a lot of carbon, hydrogen, oxygen. Note that vanilla and sugar have the same base elements, carbon, hydrogen, and oxygen, but they vary in amount and how they are physically bonded together. Sodium bicarbonate has sodium, hydrogen, carbon, and oxygen bonded together. They all mix together and you can make a cake out of it. So there are various states of matter. There are several. A lot of them are advanced. The ones that we will be doing in this class are only solid, liquid, and gas. We will not be doing anything with plasma really. For this is chemistry, we will have some plasma at one point. Well, we're going to be running electricity through a gas at one point, and it will heat up and turn into a plasma and emit light. We can characterize something as being microscopic. It refers to what you can see without a microscope. It was so-called with the unaided eye. And then we have microscopic, which refers to things that you can see, that you would see if you could see individual atoms. They require a microscope. So your skin, for example, there's a microscopic structure where you can actually see it with the hair on top of it. Then you can also look in and zoom in with a microscope and see microscopic things like the skin cells that build it up. Solids have a fixed volume and shape that result from the way their particles are arranged. So with solids, the atoms are bonded together between different, or the molecules are connected together in such a way that they are not free to move. Neighboring molecules will hold and lock the other one in place. Note that they are still moving, they're jiggling around, but they're unable to move away from their neighboring atoms. Liquids have a fixed volume, but not a fixed shape. This is also sometimes wording as having a definite volume, but an indefinite shape. So a fixed volume means that if you have 500 milliliters of water and put it into a water bottle, it will take the shape of the water bottle. But if you pour it into a glass, it's because it doesn't have a fixed shape, it will take the shape of the glass, but it'll still be 500 milliliters of water. The volume doesn't change, but it will change. But the shape will change to match whatever container it's in. How this works is the molecules they have enough pull on the neighboring molecules to keep them contained, but they are able to move past each other and slide around. So water molecules, for example, they're loosely connected, but one water molecule can move around, but what they don't normally do is get to the surface and leave, because the rest of the water molecules hold on to the water, and as it gets to the surface, it pulls it and keeps it down. It doesn't mean that some of the water molecules can't escape the water vapor. At the surface of a lot of liquids is a small amount of that molecule leaving. Gases have neither fixed volume nor shape. So if you put, for example, like hairspray, if you put hairspray, you can force it down into a hair-shaped bottle shape and have fixed volume. When you spray it, it will fill the shape, turn into the shape of the room, and it'll span. The volume changes to fit whatever container it's in, and as it spreads out. You can look at this of water, H2O. In the form of a solid, you can notice that it forms like a crystalline shape, a repeating pattern. If you look closely, you can see that it's hexagonal, where the hydrogen atom will bond with neighboring oxygen of not only the two oxygen that's attached to, but also oxygen of another water molecule will get close to it. So in the ice form or solid form, the water molecules are fixed and are able to free themselves. In liquid, they are separated but still come somewhat close. They're not really bonded to the neighbors and able to move past each other, but because the pull is so strong, they tend to stay somewhat relatively still, but they can easily flow and slide past each other. In the gas, they are very far apart relative to the size of the atom and the molecule, and for all basic purposes, they don't really interact. They will collide in with each other occasionally, bounce off of each other, hit walls. For the most part, we assume they don't really react with each other or touch. So physical changes are changes in which the identity of the substance doesn't change. Changes of state are physical changes. So going from a solid to a liquid, melting, is a physical change. So water, we need water to live. But if you're in a desert and all you have is ice, you can eat the ice and the ice will melt in the water and it acts just like water, even though it's in a different state. Arrangement of particles are, so if you rearrange it, it's still the same. It's a physical change. Examples are ice melting, salt dissolving in water, ripping a paper. So if you take some salt, put it on your tongue, it tastes salty. If you fill a water bottle with water and a lot of salt, and you take a drop of the water and put it on your tongue, it tastes very salty. The property of salt doesn't change. All you're doing is dispersing it out into the liquid. Ripping a paper is still paper. Chemical changes occur when the identity of the substances change and new substances are formed. For example, when iron rusts. So iron is turning into iron oxide. So what do you think paper burning is? Yes, it would be chemical. When the paper burns, where does it go? So paper is mostly made out of wood. It's made out of cellulose, the primary cell of a plant. Whenever you burn it, it turns into carbon, which would be the ash, and CO2, which is the smoke, along with other trace elements into it. So most of it will be turned into a gas, which will fly up away from it. Wherever's left behind will be ash, but ash and smoke are quite different than paper. You have chemically changed the paper into new elements, or new molecules. So here's an example of a chemical reaction. We will go into this much later in the year, but you need to know that on the left-hand side of the equation is the reactants on the left side of the arrow, and they are what is going to be used up in the reaction. So we have mercury oxide. It's being broken down into mercury and oxygen. Products on the substances on the right-hand side of the arrow are called products. They are being made in the reaction. So you can have one chemical, such as mercury 2 oxide, break up into mercury and oxygen, or you can have like hydrogen and oxygen come together to combine to make water. Hydrogen and oxygen would be your reactants. Water would be the product being made. So evidence that a chemical change may be happening generally falls into one of the following categories. The evolution of gas. Have you all ever done the volcano experiment with baking soda? Have you ever seen it? So whenever you mix baking soda and vinegar together, it starts producing a gas. White bubbles will start appearing up. That's usually an indication that a chemical reaction has occurred. Another example is the formation of a precipitate. A precipitate is a solid substance that falls out of solution. So if you mix two liquids together and some solid forms as a result, that's called the precipitate. The release or absorption of energy. This could be heating up, cooling down, or giving off light. So a change in temperature or the giving off of light is a good indication that a chemical reaction occurs. Or a color change in the system. If you see something change colors, it usually indicates that a chemical is being changed. So if you look, the first example is the vinegar and baking soda being mixed together. So vinegar has acetic acid in it. Baking soda is sodium hydrogen carbonate, or sodium bicarbonate. And whenever they mix together, it produces CO2 gas. And you can see it in the form of bubbles. In the next example B, the solution of sodium sulfide and cadmium nitrate are mixed together. They're both clear liquids with no color. And whenever they mix together, you can see cadmium sulfide being produced as a solid, a yellow powder that floats sinks to the bottom of the mixture. It usually is a very good indicator that a reaction has occurred. When you mix aluminum with iron 3 oxide in a clay pot and ignite it, it requires some energy. That's also known as thermite. It will produce a lot of heat and light. Another indication that a chemical reaction has occurred. Phenolphthalein, I need to get some of that because it's very useful in chemistry. It's used as an indicator. It can be used to measure the pH level, how acidic or basic something is. And it's really nice to look at. It's a very, very fluorescent hot pink. And usually it can be sitting over here, just clear liquid, and you shake it around. And as it shakes, you can actually see the color change as it turns very bright pink. And its color is entirely based on how much acid is in the solution. We'll go into that much later in the year. But if you have if you put it in a solution and see it turn pink, it's reacting with the acid. So, give an example of a physical change. That's chemical usually. That's the heat. Well, just changing its temperature. Oh, hitting. Yeah, so chopping wood. Um, so chopping wood would be an example of physical change. You're making it smaller. You know it's physical because you take one piece of wood and you make multiple pieces of wood. It's still wood afterward. Give an example of a chemical change. So burning of wood would be an example. How do you know it's a chemical change? Because after it's done, there's no more wood or less wood than when you started, and you see gas coming out. You see heat. You feel heat. It's gotten hotter, and light was given off. Any questions over the PowerPoint? All right, let's work on this together. So, melting point. First, before I go into this, let me give y'all a definition. A physical property is a property that can be observed without chemically altering the substance. A chemical property can't be observed by looking at it. You need to make it react to observe it. So, melting point. Melting point is the temperature at which a substance goes from solid to liquid. Is this a chemical or physical property? Physical. So you don't need to change water into anything else to figure out its melting point. You can freeze it and then melt it back and figure out its melting point. Can this be used to identify a substance? So if I gave you two clear liquids and I tell you one of them is water and one's something else, if you put them in the freezer and you notice that one freezes and the other one doesn't, you would be able to identify which one was water, right? So yes, you can use melting point to identify. Does it change with the amount? So does a gallon of water freeze differently than a bottle of water? No. We'll do extensive and extensive later. Density. So density is a ratio of mass to volume. Is this a physical or chemical property? Physical. Can it be used to identify the substance? Yes. Lead is heavier than most metals. Gold is much heavier than copper. Does it change with the amount of substance? No. Specific heat. It's the heat required to change temperature. There's a more formal definition of that, but this is good so far. The heat required to cause a specific temperature change. By the way, in chemistry and science, the word heat means something totally different from what we usually use heat for in common language. Heat is more accurately described as energy. The energy requires to cause a specific temperature change would be a better definition, but it's heat energy. It's thermal energy is what heat is. So is this physical or chemical? No. So, for example, water. It works both in the same way. Either the heat required to increase its temperature or the amount of heat given off as it cools. So let's say that I took and boiled a pot of water and I waited 30 minutes. Would you want me to, or 15, 30 minutes, depending on the size. Would you be comfortable with me throwing that water on you 15 or 30 minutes later? I know yes, but it'd still be scathing hot. Water takes a lot of heat energy to actually warm up and to cool off. Water, because it takes so much energy, will sit there for a very long time and keep its heat. And it takes a lot of energy. If you put water on to boil, you'll sit there and wait for 5-10 minutes for it to boil up. Now, if I take a small bit of aluminum foil, put it in the oven, how long would it take it to reach 400 degrees Fahrenheit if the oven was already at 400? It would be very fast. It would be seconds. So you can get aluminum up to a very high temperature very, very quickly. Also, if you wanted to get, if it's aluminum thin enough and you don't use too much, you could actually reach into the oven and grab 400 degree Fahrenheit hot aluminum foil, pull it out, and it would immediately cool down the room temperature super fast, not burning you. The reason for this is it has a very low specific heat. You can also measure specific heat without requiring to change the property of water. You can just see how much energy you're putting in the water versus something else. So that would be physical. You can use this to also tell the difference between different objects or chemicals. So this can be help you identify it. And it also doesn't change with the amount of chemical you have. Area usually refers to like surface area. Can't really give a description for that because it depends on the shape. You find it in different ways. It's how much surface there is. I guess that's a good definition. How much surface a chemical has. This is also a physical property. Can this be used to identify a substance? I really don't like the fact that I'm wording it with how much surface a chemical has. A material, I can't really think how much surface. So if I told you I have a mysterious material that is 1 foot by 1 foot, has 1 square foot, do you know what that chemical is? you can't really identify a substance, so no. Does it change with the amount? Yes. If I cut a piece of paper in half, it has it has less surface area, so yes, it does change with the amount. Malleable. Malleable means can be hammered. Are pressed out of shape without breaking. Would this be physical or chemical? Can it be used to identify the substance? Yes. So, for example, if you need to tell the difference between glass and plastic, plastic is more malleable than glass. You can bend plastic. So if you tried to bend glass, it would probably shatter and break. Does it change with the amount? No, because of how it's defined. It's usually done by if I had a small bit of plastic versus a small bit of glass, you'd be able to tell a difference, compare it. It's usually relative. You say things are more malleable than other things versus getting an exact number. Ductile means the ability, so able to be drawn into a thin wire. Another way of saying is pliable, not brittle. And again, this is a physical property. You don't have to chemically change it. And you can also use it to compare and differentiate between different chemicals. And no, it doesn't change with the amount. Have y'all noticed a trend in one particular column? Most things are physical characteristics. So mass is how much of a substance there is. How much substance is there. That's also a physical property. You can't really use mass to identify a substance. If I said I had a 1 kilogram of material, it doesn't tell you anything about that chemical. And it does change with the amount. Flammability is how easy it is to be ignited. How easy it is to catch fire. Is this a chemical or physical property? Chemical. You cannot look at a clear liquid across the room and know if it's flammable. And if you needed to do some test to see if it's flammable, the only way is to actually catch it on fire. And when you catch it on fire, you're chemically changing it. So if I ask you to go test a few drops of gasoline and see if it's flammable, once you catch it on fire, you have no more gasoline. So you end up changing it when you try and make this observation. Can this be used to identify the substance? Yes. If I ask you the test between water and alcohol, you can take a lighter to one. One of them will catch fire, the other won't. And no, this does not change. Porosity, or viscosity, is how is like fluid thickness. How easy it flows. This is also a physical property. Syrup versus water. Yes, this would usually be used to help identify. And no, it doesn't change with how much. Miscibility is the how able it is to mix together. For example, oil is not miscible in water. Oil won't mix with water or float on top. This is a hmm? So is this chemical or physical? Yes. You wouldn't say if two chemicals are reacting together that one was miscible and the other because they're reacting. This can also be used to identify it. And no, it doesn't change with the amount. Boiling point is the temperature at which a substance goes from liquid to gas. And this is, again, a physical. Yes, it can change. That's one of the primary ways of extracting and separating chemicals apart, is boiling off one chemical and throwing away the gas, or collecting the gas and turning it back into a liquid in a different container. And no, it doesn't change with the amount. Odor is tricky. Odor is smell. This can go either way. It depends on what you mean by odor. So if you think about odor, what's going on is a small bit of the material is evaporating, going into the air. It's then attaching itself to your olfactory nerves in your nose. The olfactory nerves does a bit of chemistry on it and causes a neuron fire. This neuron firing is a chemical reaction, if you know biology and how neurons work, which then causes it to send via chemical reactions across the neuron all the way to your brain. So all the way through, it's chemical, but I will treat this as physical. Oh, sorry. The reason why is if you had, for example, perfume in a bottle and it's clear, you can identify it by smelling it without really chemically altering it. But another thing is you really can't identify. So let's say you had it in a sealed container. Another reason why odor is sometimes called chemical is you have to destroy some of the sample. You have to breathe it in order to identify it. And once you breathe it in, it's lost forever. So in some sense, odor is chemical in the sense that you are losing and destroying some of the sample. You're altering it. But for purposes of this class, I'm going to say it's physical because you can use it to really, you're only doing a very small sample. Yes, this most definitely can determine what it is. And no, it doesn't depend on the amount you have. Volume is how much space something takes up. This would be physical. And no, you can't really use that to figure out how much something is. You can use both mass and volume together to figure out density. You can use density. But if I only told you volume, like I have 500 milliliters or something, you would not be able. Any questions? Alright. Other class got to there and we had to stop. Kind of went a little faster in this class because I also figured everything out during then. Yeah, or not. I keep y'all saying. That's it for the day. We'll continue the packet tomorrow.